Hello, welcome to my channel. In this video, we are going to talk about the zero crossing detection. So to understand this, we are going to create a different problems with the same set of input data. So this is my input data, t is the time, x is my input which is changing from 1 to 0, y is some output, calculated output, which is to be transferred as it is when x is equals to 1. And if x is equals to 0, then we will be sending our default value 0. Let's design this quickly. So I'm going to first import this data. I'll go call for this file. Then I just need these three data. So I will select these three columns and then I will change this as a column vectors. So all this individual data will be selected and input. So t, x and y 21 by 1. This is the column matrix. Okay. Now close this. Let's go to Simulink. Okay. First here I'm going to import those data which I have imported into the base workspace. So transferring from base workspace to the model workspace. So I'll go import, load from workspace, input. I'll say this will be my x and this will be my y. Just apply. Okay. Now I am going to design this input, switch, scope, constant, zero value. Okay. So this input is my x connected to switch criteria condition. Then this is my y as a if condition passes, then else part zero value, and then I'm going to create the scope for three inputs. So I will go over double click properties, then configuration properties, ask for three inputs, design this layout vertically, apply, and then OK. Then connect this first x, then y, which is as it is coming. Then this is the calculated. This calculated I also want to send back to the base workspace. So I'm sending to two workspace and I will give this name as y. Right. Now going back over here, as I said, I'm going to create 4 different scenarios. So first, fixed step solver with no zero crossing. We'll see how this will come. And then solver should be discrete type and step size 001. Okay, going back over here, if you see double click, here you see enable zero crossing detection, because by default whenever you create your model, the solver selection variable step. So I will go over here in the solver. I will say instead of variable step, I want fixed step, and then here I want discrete with the 0.01 fundamental step size, and the maximum iteration will go for 0.2 from the Excel sheet. So here you will see 0.01 of increment every time, and the maximum value we have 0.2. Okay, with this, let's apply this and execute. Let's see the result first in scope. Scope shows whenever my x is 1, I am sending out.y as equals to y value. So here increment till here. Then when my x became 0, I'm immediately setting my out.y as 0. And again, if x become 1 value, then y value, x 0, y become out.y becomes 0. Looks correct. So now we will go to the base workspace that we have already exported the data to the base workspace. We'll click on this out, and then this is my y which I'm calculating. So I'm going to copy this and paste it over here for the comparison. Now we will go to the variable step solver and we'll see how this zero crossing will come, because when we have selected fixed step, this zero crossing has disabled automatically. So here, when I have selected my fixed step solver there in my properties, this became disabled. Now I will go back, and if I will make this change as a variable step, and then solver I want as a discrete, and maximum step size that I want to give is 0.01 again, and then apply. Here, if I come back here, you will see this got enabled. I will still keep disable this, apply and execute this solution. Now if you plot, you will see this will go as a continue, because whenever you use a variable step solver, the input data, all the data becomes in a state of continuous. That's where you do not see vertical transition between 0 and 1, and here it's changing 1 to 0 in a continuous manner. Let's go to out data, what it has been reflecting now. So just refresh it once and reopen. You will see the same result we are getting over here. Just copy and then paste it into my this variable step solver discrete and step size 001. So this is what we have executed. Now in the next case we are going to enable this. What we are going to simply do, we are going to open this and enable the zero crossing, apply and just run this. The simulation result you will see over here looks almost similar, but now we will go to our base workspace and see how the results has been changed. Now here you will see some results has been changed. Well, first copy and then paste it here. So variable step solver, solver discrete, step size 001 and enable zero crossing, paste it over here. Then we will take one more step, then we will explain about the zero crossing. So here what I'm going to do, I'm selecting variable step solver, enabling zero crossing. Solver will be auto now this time. Instead of discrete, I'm going to use auto, and step size also instead of 0.01, I'm going to change it to auto. Let's do this one change and then again we'll come back to this Excel file. So here variable step is correct. Here I'm going to give auto, and okay, for auto we don't have to give anything, so just apply and execute this. Okay, again scope will look almost similar, some changes will be there, but main our interest would be in the result. So we will go over here, we will see this, copy and then paste it over here. Okay, then one more which I couldn't get the result of change, which I want here is variable step auto discrete, and here instead of auto I want to see auto and then apply and then execute the result. It should show me something different. What I want to show is the another part which I'm not getting with this. Okay, so this is what I want to explain as the last part. So I will copy this and then I will copy paste over here. So let's do this comparison later. We'll copy this, paste, and instead of, okay, we'll merge this first, copy, this will wrap. Okay, variable step we have, enable zero crossing we have, solver instead of auto, here it was a discrete, and then step size auto. Okay, now let's understand what differences we are getting from this simulation, different simulations. So first I was having some data with fundamental step size 0.01, and then I was getting some x as input data. Whenever x is 1, y I am sending as output to my simulation output should be equal to y, and whenever x is 0, simulation output should be equal to 0. So in the fixed step, without any zero crossing detection and then step size 0.01, everything is happening as per the expectation, which even we can calculate by ourselves. So my x is 1, then here x is 1, then 20 should pass, If x is 0, then 0 should pass, right? Now, in the second step, I have changed my solver to variable step, but still I have kept that zero crossing detection disabled so that my behavior will be same as the fixed step solver. So here if we see number of steps taken exactly same, results are same. Here you will see exponential values which are matching to the simulation y values for the fixed step. Right here it is 60, here 60, here 0, here 0. So everything same because the zero crossing is disabled. Now in the third simulation, what I did, I have selected my solver as a variable step and enabled zero crossing detection in the switch block. Rest properties I have kept it as it is. But here some simulation three. If we see these four simulations are more, right? Why this happened? Because here you will see when it was 1 there was a good solution, no extra processing. But when this 1 has been changed to 0, so for the first step it was a 1, for the next step it was 0. This is called as my zero crossing detection. So for the 0.01 it got executed and calculated 20 value. Then for 0.02 to calculate 30 or calculate 0 value, it took more time to identify the change point. So this 0.02 which you see over here, it is actually 0.0199 and so long value, but not still not equal to 0.02. And there solver has took one step more extra to calculate and got 30 value because it was not at 0.02. My result should show 0 at 0.02. I should get 0 value because x became 0. So here at 0.02, x became 0 and y became also 0, output y. But this is my additional step. Now why this step came. So if we go to our paint, here I have drawn, this is my x step time and this is my y-axis with the x value. X value is changing between 1 and 0. Very simply I have plotted something, x is 1 for some time and shifted to 0. So this point, if I change the color, so this is my point of zero crossing detection. Here my x value changed from positive integer to 0, or else in other case it would be from negative integer to 0. So whenever the value changes from positive integer from negative integer to 0, that point will be called as zero crossing detection point, and that point will be considered as a critical point. There solver will take one or two or depends on the solver some more steps extra to change what is happening over there. So this we call as a crucial point of detection where more steps will be taken to calculate the fluctuation between the output value. So again, if I explain for this first two, here the input was constant 1 and 1. So solver identified there is no much change in the input and process as it is very easily. But in the next step from 1 to 0 change happened, then solver identified this is a crucial point. Here I am getting the zero crossing detection. Then I will take one more step extra to change identify the change point, and there I will show. So that's why it took one step extra for this particular timestamp and then next step on this particular timestamp. Let's see where is another zero crossing detection. It would be here, right? Because we have this. So let's bold these colors. Here, this is again a zero crossing detection. This is again zero crossing. So between 0.03 and 0.04, we see one more zero crossing detection. So we'll go over here. So first we'll check whether what is this value. This is 0.03. 0.03 should show 40 value, no, 0 value because x is 0. So which is correct. Now this is again looks like a 0.03, but when you click on it, you will see this is not exactly 0.03. This is 0.03 and then so many zeros and the last two, but more than 0.03 exactly. And there itself, my solver has identified the value has been turned to 40, which in our perspective looks which is only 0.04 actually. but solver has taken one more step extra, and just after very 0 point, sorry, this to this, after just very small change of so many zeros and then 2, it identified new value became 40, right? So this is another zero crossing detection happened, and here solver took one more step extra. Similarly, if we see again, this will be my zero crossing detection, right? So which is between 0.05 and 0.06. So let's go to 0.05. So 0.05 is processed, identified as 0.05, and then again so many zeros and then 2. And this 0.06 is again with some shifted value. So wherever this zero crossing detection happened, here solver has taken their own effort, additional effort to identify the change point, and that's why the number of steps has been increased. So the total 4 steps has been increased because the zero crossing detection has been identified, and then steps has been accordingly changed. Now we cannot identify these change points by ourselves. This is a solver definition. Solver is somewhere identified and then took some extra effort to compute it, right? Now in the next step, what we did, so same settings we have kept it, variable step, then enable zero crossing detection, but here we have also changed the solver. Instead of discrete, we went to solver auto, and step size also auto. So we have not mentioned solver to go for the which solver. Then solver automatically detected the problem, simulation problem, and defined which solver will be okay, and gave the step size also they have defined by themselves and given the same result. If hardly one or two value might have changed, but I don't see over here everything is same, right? But in the last problem, which I want to show additionally, where too many steps has been detected. Why this happened? Because here I have given my solver as a discrete solver, but I have not given any step size. So I have said use particularly discrete, but your step size will be self-calculated. And here they have randomly calculated values, step size very differently. So that's why there are too many steps. And also the simulation output you will see, which is nowhere in my input data set. So y doesn't have any 14 value, but you will see the y is calculated as 14 value. So this solver completely differently works. So I don't know the mathematics behind of this. So hope you understand. At the end, I will just repeat myself with the zero crossing detection in 2 lines. Firstly, it will be detected on your positive integer change to 0 or negative integer change to 0. This point of detection will be called as zero crossing detection. Secondly, this will be crucial point, and where simulator will take more extra steps to simulate and find out the change point and replicate into the simulation result. And this will be only applicable for the variable step solver, where you have choice to disable it, but it will not come for the fixed step solver. It will be always disabled there. So thank you so much for watching. Hope you understood this, and I would say you do more experiment, select different solvers, different properties, and you will find some other result. If you find any other conclusion, you can comment in this chat box. Thank you so much for watching.